A very warm good morning to one and all over present here. It gives me an immense pleasure in welcome all of you again. I hope you are doing well. We learned a lot many things on yesterday, like quantizations, pruning, and many more. On behalf of the organizations, I again welcome you all on a lecture series, online webinar on an overview of AI, its component, system, and application, organized by E-Infochip, Aero Electronics, and Asia Gujarat chapter. I kindly welcome our today expert, Mr. Sujeeth. Sujeeth is a VP of Engineering at Zentry Lab. Without wasting too much of time, I'll hand over to Mr. Sujeeth. Thank you.
Thank you. Hi all. Just today I would like to introduce you these transformer models now, which is a basic building block element to build modern conversational systems, especially you are seeing ChatGPT or most of the recent time stuff I can say. So this discussion or presentation is introducing that concept, actually how it works, actually what are the different components are there in this transformer model. It would be useful for most of the beginners, actually I can say. So moving forward, now a high level look, actually when we look at it, right, okay, when you want to translate French to English, let us say that, okay, and I don't know how to pronounce this input, but the output of it is I am a student, actually, right? This is the expected thing. So the transformer, when you give an input, you are want to get a translated output. Similarly, there are various problems, sentiment analysis, summarization, question and answer systems, and most of these things work on the similar lines. So a high level look, actually, when it comes to these transformers, there would be two different blocks, which we can categorize them as. One is an encoder and the other one is a decoder. These two things actually tied up together for this translation activities. So in generally, the modern transformers, the multiple encoders are stacked up, and similarly the multiple decoders are also stacked up for the translation activity for the better reliability. So from the last encoder stage, the encoder values are fed to the decoders of different stages, okay, so that the interdependencies and all will be resolved in a decoder stage, right, to predict a word or for the translation. So still continuing, when it comes to the encoder and decoder, the critical blocks in encoder is like after word embeddings, the position embeddings, the self attention is the one actually predominantly major thing here to understand, then feed forward. And on the decoder side, again, you have a encoder decoder attention model and the feed forward. On a decoder side also, you need a self attention, which is taken from the previous word generated. So a high level look through this diagram. This diagram is copied from again attention paper published, actually all attention. Yeah, I don't remember the title exactly. Right. Okay. This is a popular paper which explains you about the self attention mechanism. So the things that are to be covered today under this thing is, right, okay, inputs and embeddings, how they are, positional encoding, how we do that. And the self-attention model is and then the multi-head attention model, scaling and normalization, and feed-forward network and integrated model. Actually, how these inputs are taken and processed towards the end, right? Encoder and decoder parts. So input embeddings. First, let's pick the first one. Now here, when it comes to the input embeddings, right? Okay, the question is all about when words are given, sentences are given, right? Okay, how do we can really represent them in a vectors so that we can train the machines by using that one. So the first step towards that is always tokenizing the words. Okay, for the tokenization, you have different approaches described. Here under the slide, I have added the links, 3 links here. If somebody wants to understand it in a more detail, can read through them. Here, these are the um, typically existing models. I can say the continuous bag of words and the skip grams. When the input tokens are given and predicting a missing word, a W of T, given its surrounding words, okay, we call that as a continuous bag of words model. And the skip gram is if a word is given, what could be the its surrounding words, okay, is called a skip gram. Actually is a more of again a training a neural network models, okay, by taking the tokens of the words and feeding it through the neural network and predicting back the original. Actually, otherwise you can look at it as something as continuous bag of words are connected back to the skip grams. Let us say that I'm giving these surrounding words and I want to predict the surrounding words so that this WT is predicted well there. That case, right? Okay, so whatever this encoded representation that you get for the word, we call that as word embeddings. Okay. So typically the word embeddings can be a vector that depends on like what are the sizes, that what is the corpus size and all. Based on that, the resolution you want, that can be a 512 or different sizes are possible based on your problem. So this is about the word embeddings, input embeddings especially. So next step is positional embedding. Once is a sentence is given, now each word is represented by using a vector of some d dimensions. Now, how these are positioned in a sentence is one of the critical aspects to be added up here in the positional encoding stage, right? So positional encoding, whenever we do that, okay, position information when we want to add to the word embeddings, the positional information should these are the five points, okay, should be obeyed. It should output a unique encoding for each time step. The time step is about each word actually. T is equal to 0, first word may come in. T is equal to 1 and second word may be coming, right? Like that. That is a timestamp. So positional encoding at each time should be unique actually. It should not be repeatable. Actually, distance between two time steps should be consistent across the sentence with a different lengths, right? So if it is a k timestamps away, the distance should be k times the differences between the two neighboring things. Okay, so that these are uniformly spaced actually. And our model should be generalizing to longer sentences without effort. So you cannot plan whenever you build a positional encoding scheme. If the dimension of a vector or else the sentence length is changed, okay, it should not be it should not be something like we should rework everything. Okay, it should be extensible easily. Values should be bounded. That means we cannot the values positional information cannot be encoded into larger numbers. It must be deterministic actually. So you should be redefine it right now through a simple closed form equation. So here, looking at this diagram, let us say that the input sequence is given is I am a robot. Okay, for I we may have a position word embeddings for I. For am also there may be word embeddings. Let us say that there's a d-dimensional vector for each of these words. There's a word embeddings is done. When it comes to positional encoding, for the index of a token 0, the first timestamp, now I need a vector like P00, P01 to P0, d-dimensional vector representing that position. Okay, you may have a question also, can I use the indexes straight away, right? 0, 1, 2, 3 or something like that. But what happens with that is if the sentence length increases, the index value keeps increasing monotonically there. Actually, that will not be fully bounded. So you are using a vectors here to represent the positional information actually. So for position 1, now you have P10, P11, P1D. Now what kind of the um, vectors can be used to encode this positional information? Now this is a positional encoding scheme suggested in the attention is all you need paper. Okay, and now it is predominantly used, I can say. Let us no, the thing is that here these guys have used sine and cosine waveforms actually. At even positions they have used the sine, and the cos odd positions they have used the cos. Now you can see here, right? Okay, position of an object in the input sequence in this particular equation. Okay, there's a k. Okay, um, the ranges in 0 to L by 2. See, L by 2 is the total dimension of the vector. Okay, and the dimension of the output embedding space is the D. Okay, so you are finding out a vector of length here in this case L is the total dimensions of a input embedding vector size. So you are producing the weights as per that actually by using the sine and cosine waveforms. Here this is a 10,000 is a user defined scalar actually, anticipating that okay, maximum sequence length can go up to maximum word embeddings length can go up to that size. Till then you have no issue. Otherwise these are the periodic signals. Otherwise it would be something like uh, sine and cosine encoded based on the position. So the frequency of it is also be changing with that actually, now with the position and as well as the dimension. So it meets all the requirements of the positional encoding. So if I take this, look at this table, right? As for the given the sine and cosine formula, if I take the index of taken 0, 1, 2, 3, okay, for a k is equal to 0, where I is equal to 0 to 0, 0, the first position sine and cosine, and 1, 1, the considering the even and odd positions, right? L by 2 length, we have to take I indexing from. So now these are the weights generated with respect to the each position here. Okay, so these are the positional information. This positional information is added to the word embeddings to take it to process it further. So yeah, so far to recap, right? Now we have input sequence. Each word has a word embedding of some dimensions, okay, L or whatever. Now this input sequence has a positional information which is encoded into a vector and that is added up to the word embeddings. So now we have brought in the word embeddings and as well as the positional information together there. Now going forward, how we are using it in a self-attention model. Actually, now we have a position and we have a vector representation of a word and a vector representation of a position. Now how this is fed to the self-attention model. And in case here I have given a link actually, intuition behind self-attention mechanism in transformer networks. Okay, this J. Almer's presentation. I advise you guys go through that. That's a wonderful presentation, I can say. And self-attention when it comes to, right? Okay, self-attention block is comprised of 3 steps here. Okay, so do product similarity to find alignment scores. Basically, suppose if different words are given, how much each word is aligned with the other words. Actually, if they have a similar meaning, they should be aligned well with each other. That means when I find out a dot product, If the alignment is better, right? Okay, the dot product score would be higher. So the dot product is used here to define the alignment of these words. And then the normalization of the scores to get the weights. Okay, because so once we get these dot products, right? Okay, just you want to bring them into a scale so that you can the dynamic range will not be too much varying actually. Reweighing of the original embeddings using the weights actually. So original embeddings of the words whatever are taken mixed with the positional information are reweighed with these normalized weights. These are the three steps actually. We can abstract the self-attention model into these three steps. If we look at this self-attention model, right, to understand it, let us say that now I have a V1, V2, V3, V4, which is the sum of word embeddings and the positional information, right? Now, here the self-attention to V3, that means when these word sequence are given V1, V2, V3, V4, here we want to find out how much V3 is um, oriented with respect to the other words, basically, right? Okay, given in that sequence. Now you are computing that as a dot product. Okay, S31 is a dot product between the word vector 3 and the word vector 1 here. Okay. Similarly, now you have the projections of V3 onto every other word vector. Obviously, you can expect this S33 should be the more stronger value because that is aligned onto itself, right? Is expected to be stronger. Now, normalizing the alignment, the softmax is the um, method used here to normalize these values to bring them into the range of 0 to 1. And the sum of all the weights produced here should be equal to 1 actually. So these weights are moved into some sort of a probabilistic space from using the softmax here. So total reweighing the attention. Okay. Now I have weights produced with respect to the V3 here. Now we would like to get an attention result Y3, right? Okay. By linearly combining the weights here, right now. So V1, W31 is a weight got using a V3 and V1. And W32 is a weight we got by using V3 and V2. Similarly, W3, V3 and V3, right? Now, when I got it, the last line is merged actually here. Okay, Y3, Y31, Y32, Y33, Y34 are the weights computed here, right? Now, sorry, these are the multiplied with the weights computed through the projections we got. Now I got a new four vectors. They are summed up to produce Y3, the positional representative of V3. Now the positional information is also encoded into the, the contextual information is also encoded into Y3. First, you got a word embeddings. You have added the positional information into this. Now with the self-attention mechanism, you are bringing in the contextual information into the encoding scheme. So if this left side part, when you look at, right, it is done at a vector level. Here we see that there are no learnable parameters. Okay. Now to make this more learnable, actually, it is generalized to representing this in this earlier case, right? When the V1, V3, your V3 is acting as a query, actually. How much this is correlated with the keys provided V1, V2, V3, V4, right? So general to make it a learnable system. Now the three matrices are defined here. One is called a query matrix, and the MK is called a key matrix. Okay, and then you have a MV called a value matrix actually. Key, query, and value. These are three matrices are introduced and which are learnable. The conceptually, this first part is straightforward to understand, and to induce these learnable parameters into the system, right? Now V1 is multiplied with the MK, whereas earlier in the explanation it was multiplied with V3 straight away. Here the V1 is MK is a matrix. Let us say that V1 is a vector of dimensions 1 cross 50. Now MK will be of a matrix of dimensions 50 cross 50. Similarly, MQ is of dimensions of 50 cross 50. Now V1 multiplied with the MK and the V3 multiplied with MQ. Now it is similar to write V1 um, and finally you are computing how much of V3 is in alignment with the V1. after this learnable parameters basically. So now you are computing the weights and the same softmax is applied. When it comes to the value matrix, again you will have a 50 by 50 matrix here in case a word is of 1 cross 50. Now V1 multiplied with MV here will be producing a 1 cross 50 vector, right? Is multiplied with the weight W31. Now I got all the contextual information encoded into Y3 through this. So in a self-attention mechanism, the conceptually it is you are taking the dot products, you are measuring the weights out of the dot products, normalized weights, and then you are combining them by using the word information to get its contextual representative vector for each word. So here, by using these matrices, you are building a system where you can learn these parameters during the training phase. I hope that is clear to all. Now, self-attention, just digging into a little bit geometrically here. Now, let us say that V1, V2, V3 are the word vectors. Word vector means I'm always considering if the positional information is also added into that. Okay, there's a 1 cross 50. Now, suppose that these are the key values we can say, and V2 is a query given, and then V2 cross V2 dot product with V1, V2 dot product with V2, that gives the orientation of V2 with respect to the input words given there. And these scalars are produced and the scalars are normalized by using the softmax. And then I'll have a weights. These weights are used to linearly combine the input words actually to produce its contextual representative Y2, given a word V2. Okay, so now to generalize it, as we earlier spoke through the previous slide. Okay, now you have introduced, we are introducing here now MQ and MK and MV. Now words are V1, V2, V3. Unlike earlier, they are passed through the matrix provided MK, right? Now I have V1 multiplied with MK, still I have a 1 cross 50. V2 multiplied with MQ, still I have a 1 cross 50 vector. And then we can find out that product like earlier. Now I got a scalars, normalize them, you got the weights. And when you are combining these, linearly combining these input vectors, now you are applying a value matrix here, applied on the each word. V1 multiplied with MV, V2 multiplied with MV, V3 multiplied with MV, and then you are getting a Y2, the representative of V2, capturing the contextual information. Okay, so the self-attention when it comes to now at the top level when we write it, now 1 cross 50, now I have a linear layer of query weights, that is MQ, linear layer of key weights, that is MK, and the linear layer of value weights, that is MV. Okay, now V1, V2, V3 are passed through MQ and MK, and then it is something like, suppose if you see this, right, query and key matrices can be pre-multiplied, right? MQ into MK transpose, and this scaling factor is added up here just to keep the dynamic range in control given a dimensional space, right? And there's a normalization factor, you can say. And so weigh original words and the matrix multiplication. So here it is something like MQ multiplied with MK transpose, right? Divided by square root of dk, the dimensions of V here, okay, is used. And then you apply the softmax on it, right? Then you are passing it through the values generated through each word is multiplied with your value matrix here, right? So then the representative Y1, Y2, Y3 are produced here. Okay, here you can see, from the paper, attention is all you need. Right, okay, QKV are now the query key value matrices. Okay, matmal scale, and this masking is an optional thing here, and the softmax, and again matmal here from the. So this all boils down to the same thing. Actually, it is a better visual representation to understand it. Okay, so yeah, they're here actually. Now this is a single head self-attention model. Now to summarize, right now you got a sentence. For each word, you have a word embeddings. Word embeddings are produced by taking the by reading the tokens of the words, tokenizing the sentence, or tokenizing the words. They are maybe using a bag of words model or else the skipgrams to produce a word vectors. The positional information is encoded by using the cosine and sine waveforms. Positional information is added to the word embeddings, and then they are passed through the self-attention model to get contextual information is also encoded into the vector. That means if v1, v2, v3 are the word and embeddings with the positional information added to that, again I am producing y1, y2, y3, the representatives of v1, v2, v3 respectively. The vector size is remaining same as the 1 cross 50 here. Now 50 is not like a standard, that depends on how you are defining your word vectors and all that, what you have picked to do that, because generating the word vectors is not if we have to do it, no, wiki, we have a wiki word corpus and all that. That is a laborious task, I can say. Now you've got a lot of APIs, even in PyTorch available, even Tensor also, you also available in producing the word embeddings and all. Yes, to understand those concepts a little bit more actually, what they are doing. What you get out of this is always a vector word embedding. Positional information is anyway fixed approach in this. There is nothing like that. We should only add here. Even we can concatenate these positional information to the word embedding. Still, we can process it. And why should we use sine and cosine? Need not be actually. That is one of the wise choice that the people have made when they were proposing their algorithms. Still, you have a chance to define your own positional. You can define the positional information the way you want it, but meeting those criteria basically, right? The three criteria that was defined. So now, if you want to add, right? Okay, you wanted to, instead of doing, now you had a self-attention model as a single head there. Now, if you parallelize the same thing on the given, so you are learning these MQ, MK, and MV weights in different subspaces. Okay, the structure will be remaining, then the learning will also be remaining same, right? But after getting your matrix multiplication output here, you will be adding a one more weighing scheme on that. Okay, a matrix multiplication to produce the vectors again there. Okay, so that's how you will be combining the multiple head information produced. Okay, now let us say that here in this self-attention model, now you have y1, y2, y3 produced. Now you have like 10 self-attention heads there. Now for y1, I will have a 10 representatives. For y2, I'll have a 10 representatives. Now for y3, I'll have a 10 representatives now, right? Y1 is context encoded vector of a v1, y2 is a context encoded information of v2, y3 is that means self-attention outputs. So we can combine is all these y1 representatives from the multiple heads into a single attention, right? So you are using these multiple heads here to sample this context through the multiple subspaces. That is the idea behind it. So moving forward, this is a yeah, I missed M here in multi-head. It's looking like multi-head, but is M is missing there. Okay, fine. So multi-head self-attention. If I look at a little bit detail here through this diagram. So here, right? This is an input sequence. Okay, something is given like, okay, thinking missions is something. Thinking is a word and missions is a word. And we embed each word. Okay, let us say that the 4-length vector is used to represent each word. Okay, and the positional information is also added into that. Let us say, okay, in all encoders, other than we do not need embedding, we start directly with the output of the encoder right below this one. Okay, the thing here is, okay, now each one is multiplied with, right, okay, WQ and WK and WV to produce, right? The input vector length is 4 dimensions. When you apply this query key and value, you are transforming them into, right? If input is 2 cross 4, here are the two words and the 4-dimensional vector for each word is transformed into 2 cross 3, right? Based on the dimensions that you have picked for Q, right? Okay, you're projecting that into um, lower dimensional space. Then with respect, after this attention, now you got your Z naught representative. Okay, for uh, Z naught is a representative for X naught through a single head. Z1 is a representative for X input through the second head. Like that, you may have 7 heads here. In that case, I have Z0, Z1, Z2. Now you are weighing these things to produce a Z representative as an attention output, right? This WO, whatever is, right, combining the Z1 to Z7 are also learnable parameters uh, in the scheme. So when X is given as an input to the system so far, now you got a Z as an output. Okay. Now this is all about the multi-head self-attention model, and now it is used predominantly in recent transformer systems. Okay. Both it's used everywhere almost now. The text even used in speech and even in images also we are seeing it these days, right? Even object detection and all. Now, next, after I get an output from this self-attention model, now we have to know pass it through feed forward through. Okay, intuition behind self-attention mechanism in transformer models. This again, right? Okay, I mentioned the same thing. The J. Elmer's presentation. I found that as really a very wonderful thing to understand the basic concepts. So when it comes to the feed forward, it looks something like this. Now I have a thinking and missions X1 and X2. And now we have the positional encodings as we discussed. Now I got after adding the positional information, now I got a new X1 and X2. They are passed to the self-attention model, what we have discussed so far. Now I got Z1, Z2, two vectors out of it. Z1 is a representative of X1 and Z2 is a representative of X2. Now here, right? Now you are doing here a skip connection here where you are taking this inputs, right? X1 and X2, and you're adding that to the Z1 and Z2. That means you are boosting your positional information, adding that to the contextual information encoded through the self-attention actually. Okay. Now with this connection, okay, this is generally in a literature it is called a ResNet connection. In generally, a residual operation we are doing here. Just we are boosting certain features we may lose as we pass the data over a network. Okay. Now add addition and then normalization operation. Okay, and then you are repeating this, passing it to the feed forward. When it comes to feed forward, the Z1 is passed through a fully connected layer. Z2 is also passed through a fully connected layer, and then the data is normalized after that. Okay, add and normalize wherever this resident connection is given. Okay, you are passing that back data, adding to the vector, and then normalizing it. Okay. So this is the feed forward operation. Okay, once it is done, right? Okay, now uh, with this, right? Okay, the first encoder block can be looked at it something like this. Now, input words are given, positional information is added, passed it to the self-attention model. Now I got a Z1 and Z2. I may have a ResNet connection there, adding the X1, X information again to the Z1 and Z2. Maybe passing through the normalization and then pass it through the feed forward. There also you can have a one more ResNet connection, and then out of it, right, X1, X2 are produced. Now from the encoder 1 you are getting an R1, R2. R1 is of the same dimensions of X1 and R2 is also of the same dimensions of X2. If there are multi-head, now you can linearly combine this multi-head information into produce a R1 or similar R1 or R2 or something like this. So, and when it comes to the decoder side now, right? Okay. Now we can have, so far the encoder part is good. Now you can have a multiple encoder stacked up like that. Now it is a repetitive structure, right? Everywhere each encoder produces vector similar to your input word embeddings, right? That is done multiple times actually in a sequence. So in most of the neural networks, you might have seen it, right? A structure is repeated. Sometimes the micro blocks are repeated. Sometimes macro blocks are repeated. Sometimes compound structures are repeated. This is all about, right, boosting the synapses over time actually, through the same structure. The same thing is happening here. Encoder 1, 2, and if I remember it right, okay, this GPT-1 version, they have used the 12 encoder levels and the 12 decoder levels. Okay. Now, when it comes to the decoder here, okay, now how many you stack them up and experimentation, now you have many published results on them. Okay, you can go through them. And when it comes to here, right, the decoder stage, right, now in the first step, the encoder information is passed to the encoder decoder attention model. Okay, and then normalization and then the feed forward and add normalization. Now you can see the skip connections here there, right? Now you need different kinds of, right, what would be under this encoder. Let us see that step by step. Okay, then in the once I get the output of a decoder 1, we can also give the output of the decoder 1 is fed to the decoder 2, and decoder 2 is also fed with the encoder output. So all these things are combined together, will be producing a vector, and then linear transformation and softmax from which we can guess the words actually. So moving forward, okay, decoder side, if we suppose, let us say, now you can let me get this video be played actually, able to uh, yeah, here you can see on a encoder side, now you have an input, okay, embeddings and embedded with the signal and encoder, and you got the contextual information. And then you have this contextual information encoded into K encoder decoder vector and V encoder decoder vector, right? Okay, through, and then this information is passed to the decoders, okay, is put through the linear layer and the softmax layer to get the output. So just to, that is at the stage 1, that's how it happens. Okay, as we wanted to produce the multiple outputs here, just I'm waiting for it reflecting on your system, playing some video. Yeah, you can see this now, right? From first word you have seen that. From the second word, the same thing, right? From the encoder, you take the information, and the previous word output information here is fed into the decoder, again through the same steps followed in the encoder. Word embeddings and then pass it to the attention mechanism, and then the same steps are used here. Okay, and these information are reused actually, the previous word information, the previous output generated to produce the next output basically. So this process is repeated till the whole sequence is generated or the whole translation is happened. Okay, this is the end of sentence. When you see the special symbol there at the end of sentence, from there it can be. Yeah. So when it comes to the decoding, is a more of, right, the same steps are used here when it comes to each word, right? Okay, how do you really train your model in this case to observe the sequence of a decoder output, right? If each word is encoded as a one hot encoding or a vectorized encoding, where you have a dictionary to pick that back, right? Okay, whatever that vector is there can be fed as an expected output to the system during the training phase. Okay, so this is something where the how this position information is also used to get the data. In the encoding phase, you can see through this animation. Okay, each word is and then after the decoding phase, the information from the encoder and as well as its previously predicted words. Okay, and then they're combined to produce the sequence. So this is all about uh, um, your transformer models. Okay, now these transformer models have become very popular and applied across. And this presentation can be shared across the group in case if needed. And you get a lot of information further to go through. Okay, now let me answer any questions that you have based on this presentation. Based on this presentation. So, okay, here I don't see, or I can see them. Okay, okay. Why does positional encoding use sine and cosine both? Yeah, here, right? Okay. If I use the sine and cosine in a vector, if I want to get a different positional vector, actually, can be we can obtain that through the affine transformation vector. That means if I multiply one position vector with this transformation, I have to get the other position vector. If I use just sine or cosine, that may not be possible. So if I use both sine and cosine there, building such transformation is possible there. Why are word embeddings scaled before adding position encodings? Why are word embeddings scaled before adding position? No, word embeddings are not scaling generally before positional encoding. They are added up together as it is actually how you have built your vectors, right? The only expectation is each word embedding that you get should be uniquely representing that word actually based on its surrounding words used. Okay, what kind of scheme that you use basically, right? And then after you are adding a positional information here. Now let us say that the positional information is encoded with the values in the range of minus to one, minus 1 to 1. Let us say that. Okay, you may normalize them to bring in the vector values in that dynamic range so that it won't nullify the effect of the position information. Okay, if that is the vector, data normalization may be required if to control the dynamic range. Okay, yeah. And positional encoding without input embedding, is it possible? Positional encoding without input embedding. Positional information without, I'm not sure, I don't understand this. I don't understand this actually. Okay. Does multi-head attention remove the need for self-attention? No, multi-head attention is multiple self-attention models run in parallel. Actually, it is not removing the self-attention. Okay. And what is the difference between positional vector and the attention vector used in transformer model? Yeah, position vector is all about tells no at what position this particular word is in a given sentence, right? Okay. Attention vector is all about, which will talk about how much of significantly it is related to the words in the given sentence. That is the information encoded into attention vector basically. Okay. And what is meant by encoder decoder attention? Yeah, encoder is encoding the information, decoder is using that information to decode that in a different space. They are, they are something like, no, they're like same to same, but different kind of, right? If I say hi, hello in some language, hi, hello in other language, they are same, but they are different. Okay. There's something like that. Okay. Encoder, decoder is something. Encoder is taking something equivalent to the output that you want, but they are different actually, languages, text, whatever it may be, right? Is there any open source library to study? you got a lot of content. Um, Trust me, to make this presentation, I might have added hardly 10 sentences on my own. Okay. And every bit is copied from internet. Okay. And so you have a lot of information available. And for the beginners, actually, I say Jay Salmer, he's actually, I've seen his lecture lately. I've not inquired about where he's from and all. Let me check that. Jay Salmer, you can, the title of his presentation is something, he mentioned it as transformer understanding something is there. You can transformer tutorial part 1 or something he has mentioned that as. Okay, you guys can go through that. And you got a very good presentation from MIT as well. Okay, when it comes to the sequence to sequence mapping. And yeah, you may have to spend little time. Okay, don't just try chat GPT-3 and the rest back. No, you may have to browse a little bit. Okay, to get these videos and all for you. Okay, yeah. Thank you very much. If there's nothing further, just I'll wind it up. Yeah, one more question. Yeah. What models does the chat GPT use? Okay. See, now let us earlier GPT models. Now they have used a similar encoder and decoder architectures, right? But that is trained on the different data. Now you may have a question and answer corpus. Okay, you may have a different context summarization corpus, and all these things are trained on these models. Maybe and how they have architected completely chat GPT 3, I'm not really sure actually. They might have used many parallel models where they have might have trained the different um, there is no different architectures are possible. Actually, I'm not really sure. Actually, I'm not read anything about how they have architected it totally. But one thing I can say, the transformer based models are the spine for that chat GPT. That much I can say. Yeah. Done. Yeah. Yeah.
For projects, researcher, tech level student, tech level based on AI ML. So they will get some exploration. Or that is my first question.
Yeah. Yeah, we can actually, we have to, you want me to answer it on this or?
Yes, yes.
Okay. No, we can work on, right? Preparing a statement is also a very responsible thing, a statement of a problem. Um, I can share my email ID or this chart. If anybody is interested in working on it, I can definitely, uh, because preparing on the fly, I cannot say anything because I have to really define it, and I also have to do little bit literature survey before I make a statement, right? Otherwise, it will be off the shelf ideas. It is tough to say because something. Suppose let us say that interactive voice bots. Let us say, okay, like personalized voice bots. Let us say that, and maybe adding a speech to even the chat GPT and make it a more voice based searching. Many things are possible. But I cannot say that no one else is working on it as well, actually. What kind of innovation that you are bringing out of your thesis matters a lot. Otherwise, your thesis has a zero value, right? So we can make a sort of a group if needed. Okay, we can discuss the problems based on the candidate interest, and the caliber of the candidate also matters actually. When they want to pick a problem, right? Take a big problem and dive with that is not a wise idea. Always right. So let's see.
Uh, One more question from yes, one more question from my answer. Many students, those who are doing a BTechs, many students, those who are doing a MTech, they are participating this seminar. So the question is, which is a trending application of AI ML in which domain we can identify either in robotics or in some entertainments or in
Yeah. No, it is in every field you need the innovation. When it comes to the core algorithms that you are seeing here right now, CNNs we have seen. Now, when it comes to the generative models, GANs is another part where we are people, where you generating an image content, maybe generate imaging through the uh, descriptive words of a scene. Now, many things are there. Actually, no, it all depends on right what is interesting to one. Basically, healthcare there are so many problems. Sports analytics there are so many problems. Even underwater imaging there are so many problems to be solved. The thing is that the first major challenge here is how much of data is available for you, to train these models. That is a biggest challenge actually here. Once that is there, you have a wider options. But when it comes to the machine learning research as such, okay, now forward training mechanism, right? Okay, which is recently proposed by again a Hinton and team. Okay, and even hybrid models are using CNNs and spiking neural networks. That is neuromorphic computing is another domain where the people can focus on. The various things are there. When it comes to application, okay, it all depends on how much data they have, what exactly they wanted to do that. If they fix on that idea, but before, okay, machine learning don't treat it as something like okay, just you can train just like that. Actually, the building an intuition behind them is a more important. I feel the basics when it comes to the undergraduate level, the basics they have to focus more on. Uh, yeah, yeah, basics. What I mean by is at least if you take no. I can suggest two books here actually. One is the Ian Goodfellow, Machine Learning by Ian Goodfellow, and Machine Learning by this pattern recognition by Christopher Bishop. Okay, at least if you understand, 50% of that book is done. Okay, the maths, the behind them, you will be comfortable with from there onwards. Because at undergraduate level and at master's level, you may get a time to focus on these two books actually. The fundamentals of linear algebra and applied linear algebra, and the basic probability, applied probability. Okay, these are the few things that you may have to focus on. The machine learning is, I can say, a straight extension of the adaptive filters theory that most of you might be studying or might have studied before. Okay, yeah. There are many interesting projects. If anyone would like to connect, they can connect with me. Krunal Kapadia. Yeah, there is. Yeah, that's wonderful. We can see the Krunal Kapadia is saying there are many interesting projects. That's wonderful. Yeah.
So last question, what is a future scope? Uh, where it's in which area AI ML is most important, or simply my question is related to the future scope of AI MLs.
Yeah, ML future scope.
Yes, sir.
Yeah, just as of now, till now, right, we are seeing results in certain domains when it comes to the text analytics and the searching and these kind of. Okay, if it has to be why productized in most of the fields, actually, still people are building. Even if you take Chat GPT 3, even if you read their what is their future activity, if you ask them, okay, Chat GPT 3. No, they are still aggressively doing research and to make it more portable and domain-specific knowledge centers they want to create with the Chat GPT 3. No, so the portability and the productization, right now, every field still has to adapt it. Maybe if you have to say something bluntly, now I don't want any VLSI engineer around. Okay, let us say that. Okay, that may be one a peak side. There may be a we may not need a programmer someday totally. That means human may be limited to the creative talents. Okay, maybe avoiding the stereotype activities, right? If that can be done in every field, right? Okay, if you don't need a muscle power, you don't have a creativity, then that every such activity should be replaced maybe by ML. Okay, maybe to think aloud actually the way forward if we move on. That's what I feel. Even robotics is one of the areas people are aggressively positioning the robots in an environment that is okay, but activity a robot can perform, okay, that is a focused area. Now you are seeing it in a um, warehouses and all, in a restaurants, in a defined jobs, but can we really make it right? Okay, we may have to see a transformer movie sometime in future, I guess, in reality. Maybe something. Yeah.
Uh, Okay, okay. Thank you all. Thank you, Mr. Sujeeth, and thank you all participants. It has been such an honor to be a part of this wonderful event. On behalf of the organizations eInfochip, Aero Electronics, and ESA Gujarat chapter, I would like to extend my heartfelt gratitude to our esteemed guest, Mr. Sujeeth. Sincere thanks to all who directly and indirectly with these sessions. Finally, I would like to thank all of you present here for making the time to be with us today, helping us make this event a grand success. Thank you, one and all who are present over here. Thank you. Thank you very much.
Thank you. Yeah, thank you very much. If anything needed, just you can consult me over my email ID. Definitely, I can respond to your queries. Okay. Yeah, thank you very much.